Okay. Thanks a lot for inviting me. And today I wanted to talk about this work, which is based on this paper, which is in collaboration with Laksha Barwaj, my supervisor, Sakura Shefer-Nameki, and Apurv Tiwari. Okay, and so this work, the line on which this work is based is this fundamental idea that was really a breakthrough in the understanding of symmetries, and the idea that symmetries, we should really think of them as topological defects in our theory. And this is a very useful point of view on symmetries, because it naturally leads to a lot of generalizations. For example, higher form symmetries that are characterized by the fact that the charged operators are not local operators, but are extended operators, or higher group symmetries, which are even more exotic and mixed together standard symmetries and higher form symmetries, and non-invertible symmetries, which I will discuss in this talk. And these non-invertible symmetries have been known for quite a while in lower dimension, especially 2 dimensions, but only recently they've been extended to 4 dimensions and higher. And as you can see, there have been a lot of papers and people working on this topic recently in the last year. And one thing that I think it's important to keep in mind is that even though these symmetries may seem kind of exotic, they do appear in very familiar examples, in very familiar quantum field theories. So you don't have to look very hard to find them in theories that you know and love. Okay. So the plan of the talk is that I will do a mini review of higher form symmetries, and then discuss non-invertible symmetries from gauging outer-automorphisms, and if I have time, from a complementary approach based on mixed anomalies, and finally conclude. Okay, so as I was saying, the modern viewpoint on symmetries is that we should think of symmetries as associated to topological defects. This was really a main point in the generalized global symmetries paper by Gaiotto, Kapustin, Seiberg, and Willett. And to understand why we should think of symmetries as topological defects, we can go back to like a very classic example, which is a quantum field theory with a U1 global symmetry. And if you have a global symmetry, then you know by Noether's theorem that you have a conserved current, G mu, which satisfies the mu J mu equals 0, or in form notation, d star J equal to 0. And then if you have J mu, you can define an associated conserved charge, and you simply define it by taking the time component of the current and integrate it on a spatial slice. But if you work only in relativistic quantum field theories, and in particular in Euclidean time, as I will do in this talk, then you can sort of, instead of considering a spatial manifold, consider a more general MD-1 manifold. And so define this operator, which is obtained by integrating star J on this MD-1. And the fact that star J is closed basically translates into the fact, it's simply Stokes' theorem, that this defect, d theta MD-1, depends on the manifold only topologically. So why this is useful? This is in particular useful when you deal with discrete symmetries, because for discrete symmetries, you don't have a current, so you cannot use the usual construction. And in the case of discrete symmetries, we really take the existence of a topological defect as defining the presence of this discrete symmetry. Okay, so to recap, what we found is that to a global symmetry G, we can associate a codimension 1 topological defect. And this is going to be my notation. So the upper label denotes the group element characterizing the symmetry G, and d-1 is the space-time dimension on which the defect is supported. And all the properties of this symmetry G can be encoded in the corresponding topological defects. For example, group law corresponds to fusion. So you can take two of these defects parallel, you stack them together, and the defect that you produce is gonna carry a label GG prime, and GG prime follows, so it simply follows group multiplication in G. And as I was saying, this viewpoint of symmetry is very useful because it immediately leads to a lot of generalizations of the concept of symmetries. So one example is higher form symmetries, which are quite standard by now. And the idea is to basically change the codimension of the topological defect. So standard symmetries are associated to topological defects of codimension 1, but you could consider topological defects of higher codimension. So this DG D minus P minus 1 with P greater than 1. And so this is going to generate for you a symmetry, and correspondingly the operators that are charged under the symmetries are not local point operators as for zero form symmetries, but are p-dimensional. So the operators charged under the symmetry are p-dimensional operators. And so this is the standard picture. This is the p-dimensional operator, which is charged under the p-form symmetry with charge Q. And you can, in naturally links with the D minus P minus 1 defect associated to the p-form symmetry. And then you can shrink the symmetry generator away, and you're gonna be left with the p-dimensional operator charged under the symmetry and a phase factor that measures the charge of the p-dimensional defect under the p-form symmetry. Maybe the most immediate example of theory with this type of symmetries is free Maxwell theory in 4 dimension. So we have A, which is the gauge potential, and an F, which is the field strength. And we know that the field strength satisfies 2 equations. The first one is d star F equal to 0, which are just the equation of motions. And then we have also the F equal to 0, which is the Bianchi identity. But then since we have 2 closed currents, star F and F, we can define 2 topological defects by integrating on an M2 star F and F. So I have an operator which I call the DE for electric, which is obtained by integrating star F, and an operator which I call magnetic, which is obtained by integrating F. And this defines for me 2U1, so we are in 4 dimensions. So operators that are 2-dimensional define, generate a 1-form symmetry. And I have 2 of them, so I have 2U1 1-form symmetries. And since these are 1-form symmetries, the charged operators are 1-dimensional, so they are lines. And operators charged under the E are Wilson lines, and operators charged under the M are Toft lines. So another example of theory with 1-form symmetry is Pierre-Mills theory with gauge group G. This is, works in generally D dimensions. And this has a 1-form symmetry, which is given by the center of the gauge group. And these higher form symmetries can be gauged like standard symmetries. And it is well known that if you take a theory with gauge group G, and you gauge the 1-form symmetry, which is given by the center, you obtain a theory which now has gauge group G mod the center. And of course, you don't have anymore the 1-form symmetry because you gauged it. But what you can show is that the gauged theory has a quantum dual symmetry, which is a D minus 3-form symmetry. And this is given by the, essentially the Pontryagin dual of the center of G, which is just a group of irreducible representation of the center. And since the center is abelian, you get a D minus 3-form symmetry, which is again given by the center itself. So they are isomorphic. And this is a general factor that it's important to keep in mind since I will use it. and which says that if you gauge a p-form symmetry in your theory T, in the gauged theory, you will get a dual D minus P minus 2 from symmetry. Okay. And another direction in which these symmetries can be generalized is non-invertible symmetries. And so for higher form symmetries, what we did was change the codimension of the topological defects. But another modification that you can do is relax the group structure. So you can consider topological operators that satisfy a more complicated fusion algebra. So you bring two of them together and you don't get a single term on the right-hand side, but a sum of terms. So it may happen that for one element, you don't have an inverse, and that's why these are non-invertible symmetries. And these, as I was saying, were known already, especially in 2 dimensions, but have only been recently extended to 4D. And these are the main construction that there have been recently. So the first one is non-invertible symmetries from mixed anomalies. That was first shown in this paper. And here the idea is essentially that you have a theory with 2 symmetries, let's say G and H, and these symmetries have a mixed anomaly. And the idea is that if these mixed anomalies of suitable type, by gauging, for example, H, you can make G non-invertible. Then there is this construction, which is also kind of related to the previous one. And here the idea is to take a theory with a symmetry G and gauge G only in alpha of space-time. So since you gauge G only in alpha of space-time, this is going to produce for you an interface between the original theory and the gauged theory. But if you also assume that the theory is self-dual under gauging G, so it actually goes back to itself after gauging G, this interface between the original theory and the gauged one becomes a defect in a single theory, and you can show that this is non-invertible. This was explained in this paper. Then there are condensation defects, which I will mention briefly later. And then another construction is what I will talk about, which are non-invertible symmetries by gauging outer-automorphisms. And all of these constructions are kind of overlapping in some theories, but all have different ranges of applicability. So what's the idea of non-invertibles from outer autos? So the starting point is a theory, a quantum field theory, that only has invertible, possibly higher form symmetries. And you also assume that your theory has a zero form symmetry, G0, that acts as an outer-automorphisms, and in particular that acts on the higher form symmetries that you have in your theory. So it induces an action on the topological defects for these higher form symmetries. And the idea is that if you gauge G0, the resulting theory, T mod G0, will have non-invertible symmetries. So some examples are, for example, Z2 in spin 4n is a Z2 outer automorphism, and if you gauge it, you go to pin plus, and this will have non-invertible symmetries. Or charge conjugation in U1 Maxwell theory, you go to O2 gauge theory that has non-invertible symmetries. And there are even, with this construction, you can also do non-abelian examples. So spin 8 is kind of special and has a non-abelian outer automorphism group. If you gauge it, you can show that the resulting theory has non-invertible symmetries as well. So to understand the basic idea, we can go back to Maxwell example, again in 4 dimension. And remember that Maxwell theory had the 2 U1 one-form symmetries. And let's just focus on the electric U1 one-form symmetry. So these are topological defects that are 2-dimensional. So are these D2 theta, where theta is a label in U1. But this theory also has a zero form symmetry, which is a Z2, and it's just charge conjugation. And this symmetry acts on the one form symmetry defects. In particular, it sends an element D2 theta into an element D2 minus theta. So the picture is something like this. You have, suppose that this is the topological defect for the zero form symmetry. And if you pass a d2 theta through it, it will emerge as a d2 minus theta. And notice that in particular, since it switches theta and minus theta, it leaves d2 pi and d2 0, which is just the identity surface invariant. And now we can consider gauging this Z2 symmetry and go to the O2 gauge theory and ask what are the topological defects that survive in this O2 gauge theory. So first of all, the identity and D2 pi are gauge invariant, so they will of course survive. And notice that D2 pi satisfies the Z2 fusion rules. So if you take D2 D2 pi, you're gonna get D2 2 pi, which is just the identity. And in particular, so D2 pi generates a Z2 one-form symmetry. This is expected because we know, remember that I told you that every theory with gauge group G has a one-form symmetry given by the center. And indeed, O2 has a Z2 center. So we expected topological operators generating a Z2 symmetry. But actually, we can consider more topological defects that survive in the O2 gauge theory, and they are these S2 theta. And the point is that the other defects that survive must be, you have to be able to write them as gauge invariant combinations of defects in U1. So in particular, if you take the sum of D2 theta and D2 minus theta, this is gonna survive the gauging because it's gauge invariant. But it's very easy to see that if you now consider the fusion of two of these guys, they're not gonna fuse into a single element. So if you, for example, take S2 theta and S2 theta prime, you can just plug in this expression and see that what you get is the sum of two terms. So this is an example of non-invertible fusion rule. Okay, and so in this example, I discussed what happens to topological surfaces, but this is not the whole story. And the point is that since you're gauging a zero form symmetry, remember that we also have a dual symmetry, which is a D minus 2 form symmetry. And in 4D, this is generated by lines. So we also have to consider line defects and not only what happens to the surfaces. So in general, if we ask what are the topological defects in the gauged theory, these are given by the following. We have dual lines that generates this dual symmetry, and they are gonna be labeled by an element R in the Pontryagin dual of G. Then we have invariant surfaces surfaces of the original theory that you can write as gauge invariant combinations. So they're gonna be labeled by an element O that denotes an orbit of the G0 action. And then you have surfaces related to the above by what it's called condensation. So I will briefly try to explain it. Condensation defects are obtained by performing what is called a generalized gauging. And the idea is this, that for a p-form symmetry, you can introduce background fields. Let's consider a discrete p-form symmetry. You can introduce background fields like for a standard symmetry, and they are given by these p+1 forms that lives in this cohomology group. And to gauge the symmetry, you simply sum over these background gauge fields. But since essentially what you can do is use Poincare duality to view this sum over background fields as a sum over the dual cycles living in this homology group. So the LD minus P minus 1 cycles. And these are precisely the cycles on which the topological defects associated to the symmetry are supported. So the upshot is that gauging a discrete p-form symmetry is actually equivalent to summing over insertion of the corresponding symmetry defects. And normally what you do is that to gauge a symmetry, you put a network of these topological defects and you put it on the whole space-time. But what you could consider is also put a network of these topological defects only on a submanifold, Mn. And if you do this, this is going to define for you an n-dimensional defect, which is called a condensation defect. So these condensation defects are essentially obtained by gauging a symmetry, but not gauging it on the whole spacetime, gauging it on a sublocus of spacetime. Here, for example, I take a symmetry generated by these green lines, and I put the network only on a surface, not on the whole spacetime. And this defines for me a condensation surface. Okay, so let's do one more example, which is spin for n theory in 4 dimensions. This has a one-form symmetry, which is Z2 times Z2, where S is for spinor representation, C for cospinor representation. We also have a diagonal subgroup, which is gonna be a Z2V for V, the vector representation. So correspondingly, we have 4 surface operators, which I call the identity S, C, and V. And then you also have a zero-form symmetry, which acts by swapping these 2 Z2 factors, S and C, and leaves V invariant. And now we gauge Z2. We gauge this Z2 zero-form symmetry, and we go to P plus for n. And we ask what are the topological defects that we obtain in the P plus theory. So as I was saying, we have the lines generating the dual symmetry. In this case, we have D1 minus that generates, I call it D1 minus, and it's for the 2-form symmetry. And then we have surfaces, which are the identity, V, which is left invariant, so it survives the gauging as it is. And then we have this D2SC surface, which is the sum of S and C, which is again gauge invariant because those 2 are switched. And then I also have condensation surfaces, which I denote D2Z2 and D2VZ2. And these are obtained by putting a mesh, by gauging the symmetry generated by this D1 minus line on the identity and on V. Okay.
Now you roughly have 3 more minutes.
Yeah, okay, I will try to wrap up. Okay, and so let's consider the fusion D2SC. Suppose that we want to determine this fusion. And the naive answer, what you can say is just, okay, I plug in the expression D2S plus D2C, and I try to compute the fusion. And what you get is 2 times the identity plus 2 times V. And what we showed in the paper is that this naive answer is not quite true, and that if you actually carefully study also lines operators, not only surfaces, what you can determine is that the fusion is actually the following. So SC fuses with itself to give the 2 condensation surfaces. So the upshot is that you can fuse 2 non-condensation defects, and their fusion can create condensation things. And this example is nice because you can also check it with an alternative approach, which is based on mixed anomalies, which, okay, I don't think I will have time to explain it, but essentially using this, you obtain exactly the same result, which is a nice check for both the 2 constructions. Okay, and to conclude, so we found examples of these symmetries in very familiar gauge theory examples. So this is very nice. It means that things are more complicated than we thought, and even simple theories have these strange symmetries. But many of the works so far have focused on like finding examples of these symmetries. And of course, what very nice is to find some physical implications of this non-invertible. So derive new constraints on the dynamics of theories coming from non-invertible symmetries. So these are topological, so you expect that they are still conserved along RG flow, and so maybe use some anomaly matching. There have been some works, so these ones, for example, but there is, I think, a lot to be done in this direction. And then on another completely different note, the mathematical structure that we expect to describe these, in general, the set of topological defects in a theory is a higher fusion category. And higher categories are not even on super solid ground in mathematics. So it's a topic still in development in mathematics. And this is maybe one of the direction in which studying these higher categories from a physical point of view can also give an input on the mathematical construction. And then what we are working on now is to extend this construction beyond zero form symmetries and in general more complicated theories with anomalies and things like that. Okay, that's it. Thanks.
All right, let's thank Leah for giving an excellent talk. Are there any questions? Ling?
Hey, hi, Leah. Sorry, somehow I cannot turn on my video, but can you hear me?
Yeah.
Thanks for the great talk. I had a question regarding so the last point that you made about the fact that the symmetric version of the S and C defects. So the way you wrote it here in terms of like a sum and sort of suggesting that you would naively expect this just to split according to some product rule. Does that mean somehow that after the gauging, I should not be thinking of this D2, which you label SC really as just a stacking of D2S and D2C, but really there's something happening, on top of just stacking them?
Yeah, I think the point is that this is why I put the spin for n label here, which is like D2SC would be a composite object in the spin for n theory. Or you can actually write it as a sum of S and C, but once you gauge Z2 and go to pin plus, then D2SC becomes really a simple object in your theory. So you cannot write it as a sum of other object in your theory. So yes, in spin, that becomes a simple object. In pin, sorry, D2SC becomes a simple object. Then you can sort of use the fact that you know diffusions in spin for n to guide your answer. But but the story is then more complicated because the diffusion cannot be derived immediately from that. But at least this tells you that of course here on this right-hand side, you expect only to come defects from the identity and V. So you cannot have another SC appearing. So this fusion would tell you that, but then you have to do a more careful analysis.
Okay.
Yeah.
Okay, thanks.
Thanks.
Is there any other question? If not, can I ask you one very naive question? Can you expand on some dynamical constraint that you can obtain from the non-invertible symmetries? Like, is it really different from typical dynamical constraints that we obtain from invertible symmetry, or is it easy to see?
Okay.
Yeah.
So let me see. Okay, I'm not sure because these are not my papers, but yeah, I think in one of you can use them as sort of, if you find that, for example, an anomaly, I guess, involving these, like the first consequence was in one paper where with the presence of these, after finding these non-invertible symmetries, they could argue if a theory could flow, for example, to a trivially gapped theory or non-trivially gapped. So the presence of these non-invertible symmetries and anomalies can tell you, for example, that you cannot flow to a trivially gapped theory. You must have something EIR. Then in this paper, they found new compactifications, I believe. So they study twisted compactifications using non-invertible symmetries. And in these other papers, they use something like anomaly matching, but I don't know the details. I think simply like in these papers they use the fact that they have non-invertible symmetries to derive terms in the action. For example, the pi zero in gamma gamma decay, they managed to rederive it from non-invertible symmetries. But like, for example, like this paper is very interesting because they actually derive the pi 0 and gamma gamma from non-invertible symmetries. But new consequences are not known. So like even this very interesting result is re-deriving something that was known already for a long time.
I see. That's really cool.
Yeah, it would be really cool to find like truly some new implication of these symmetries. Or I don't know, maybe someone can prove that you can't derive anything new using them. I don't know. it would be cool.
Right. Is there any other question? Okay, then before we end the talk, if you want to give a